Welcome to Understand the Math. In the video description, you'll find a link to guided notes that can be downloaded and filled in as you follow along with the video. In this video, I'm going to define what it means for two triangles to be similar, go over the 3 ways two triangles can be similar, and complete 2 common application problems that utilize similar triangles. Two triangles are said to be similar if they have the same shape, but not necessarily the same size. There are 3 ways that two triangles can be similar. The first way is when their corresponding angles are equal. And you can see in our picture, the corresponding angles are equal because they have the same variables. We typically label this type of similarity as AAA or AA. That means all 3 angles are the same, or if we have 2 angles that are the same, that implies that all 3 angles are the same, because all 3 angles have to add up to 180 degrees. The second way two triangles are similar is when their sides are proportional. The way that we would write this mathematically is we would say that A is to B as big A is to big B. That means those sides are proportional. And then we could say A is to C as big A is to big C. And then lastly, B is to C as big B is to big C. And we'll use that type of mathematics a lot when we talk about proportionality. Let's label this type of similarity as SSS, meaning all 3 sides are proportional. Before we go on to the third way, I want to make a note to let you know that if a triangle has corresponding angles that are equal, that also means that its corresponding sides are proportional. However, if we have a triangle whose corresponding sides are proportional, that doesn't necessarily mean that the corresponding angles are going to be equal. Now let's talk about the third way that two triangles can be similar. The third way is when we have one pair of corresponding sides proportional and the angles between them equal. You can see in our diagram here of the two triangles that we have one angle that's equal, and that's notated by gamma. And then we can say that the corresponding sides are proportional by saying that A is to little b as big A is to big B. Similar triangles provide a basis for understanding proportional relationships between corresponding sides and angles in diverse geometric shapes. There are a lot of problems that can be solved with similar triangles. Let's now look at 2 of these examples. In our first example, the sun shines on a person that is 6 feet tall. So let's go ahead and underline that. And the person cast a shadow of 2 feet. At the same time, the sun shines on a building and it casts a shadow of 12 feet. And we want to know how tall is the building. So in our diagram, you can see we have the building with a person and then the sun shining on both of them. From this diagram, we can write down a picture with the 2 triangles in it. In the smaller triangle, the person is 6 feet tall, so we can go ahead and label that as 6 feet. And the person's shadow is 2 feet. And you can see already that this diagram is not drawn to scale, but we won't worry about that. The building is what we don't know, and we're going to notate that with the red. And let's label that as X because that's our unknown. And then the shadow that the building casts is 12 feet. So we can label that one. Now what we're going to do is break these 2 triangles apart and label their corresponding angles and side lengths. So the larger triangle, we have X and we have 12. And the smaller triangle, we have 6 and we have 2. And let's notice that both triangles share a common right angle. Not the same right angle, but they both have a right angle. And then we also notice that they share a common angle, which we'll call alpha. So because of this, all 3 angles are equal in these triangles. And that means that the sides are going to be proportional. So we can write the proportionality of the sides as X is to 12. The side on the left is to the side on the bottom. As when we look in our smaller triangle, the side on the left is 6 and the side on the bottom is 2. We can then multiply both sides of the equation by 12 and we'll get X is equal to 3 times 12, which is 36. And let's include units on this. This is 36 feet. And let's go ahead and box that. So by using similar triangles, we will able to determine that the height of the building was 36 feet. In our second and last example, we're asked to calculate the radius of a cone that's given in this diagram. You can think of the blue part as perhaps water that might be filling up part of the cone. In the picture, you can see that we have 2 triangles which are broken apart below. So let's go ahead and let's label the side lengths of the triangles. For the big triangle, our top is our radius, and that's actually what we want to find. The left side in our big triangle is 10 centimeters. And then on our small triangle, the top part is 6 centimeters, and the left-hand side is 4 centimeters. Let's now notice that both triangles have a right angle, and then they also have an angle in common, which we'll denote like that. So if they have 2 angles that are equal, that means the third angle also has to be equal. So that will tell us that the sides, the corresponding sides, are going to be proportional. So we can write that proportionality as R is to 10. The top side is to the left side as in the small triangle, the top side is to the left side. We'll multiply both sides of the equation to solve for r. So r is going to be 6 over 4 times 10, which is 60 divided by 4. So our radius is going to be 15, and let's check the units. We're working with centimeters, so we write down 15 centimeters. And we will box that answer. So just like in the first problem, we were able to use similar triangles to be able to find out one unknown quantity in our problem.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.